introduction to deal with binary class classification or more general multi-class classification. So in the rest part of this chapter, we are going to talk about how to extend logistic regression from two class to multi-class classification. So in this slide, I list the difference between two-class classification and multi-class classification. In two-class classification, in a two-class classification task, we just use a logistic sigmoid function to formulate the posterior probability for the first class. Because the posterior probability for the second class can be written in this form, 1 minus the posterior probability for class 1. This trick is no longer cannot be applied for multi-class cases. So in multi-class classification, we need to use a softmax function to replace the logistic sigmoid function. I guess most of you remember the softmax function because we specified this activation function last week. So let's look at the difference. In binary class classification, we just formulate the posterior probability for the first class. However, in multi-class classification, we need to formulate the posterior probability for each class K. So let's look at this equation. For each class K, its posterior probability is denoted by Yk. Yk is the posterior probability for the class lowercase k, so please remember this notation. And its formulation is specified by a softmax function, exponential of something in the numerator, and we use the normalization term in the denominator. Okay, there is some operator over each class J. So this is the standard softmax function. As you can see here, for each class K, we need to learn a weight vector Wk. So if you are dealing with a 5-class classification task, there are 5 classes. We need to learn W1, W2 to W5. We need to learn 5 weight vectors, 1 weight vector to be learned for each class in order to calculate the softmax function. Okay, so in the following, we are going to talk about how to replace logistic sigmoid function by softmax function during optimization. Okay, so in this slide, let's compare the objective function from the original two-class classification problem to multi-class classification task. So I have specified the likelihood function for two-class classification. There is a product operator over data because data are IID. There is just a single product operator in the objective function, and we use the trick to combine the two cases for data belonging to class 1 or class 2. Now let's look at its generalization to multi-class classification. To begin with, let's consider the value, the notation used in the following. Please recall that if we are dealing with a capital K class classification task, each label is a Boolean vector, and the dimension of this Boolean vector is capital K, 1 for each class, and all the elements are 0 except the ground truth the ground truth class, the corresponding element is 1. So it is a Boolean vector, which is just exactly one non-zero element, which corresponds to the ground truth class. Okay, so we use Tn to denote the label vector, the Boolean label vector for each training data n. Now let's look at this notation. There are 2 indexes. We need to consider training data index n and class index k. So for each training data n, for each class k, we use this notation ynk to denote this one. So what is the meaning? This is the posterior probability for class k and for training data n. So this is the posterior probability. We use ynk for short. Now we would like to consider the extended likelihood function. So we need to optimize capital K weight vectors, 1 for each class. Now let's look at the objective function. The objective function, let's look at how to derive from the second one to the third one. I think it is straightforward because we use ynk to denote the posterior probability of data n and the class k. So it is this notation, the conditional probability given the given training data n and its posterior probability for class k. So this is the so-called posterior probability, and its definition is given here. So it's ynk to the power of tnk. Now let's look at this one and this one. This is used for binary classification, and this is used for multi-class classification. Let's look at the same part first. There is a sum operator over training data, and the n is the data index. So there is a product operator over the training data. So this is the layout the same here. However, for multi-class classification, we introduce the second product operator, which is over all possible classes. So k, lowercase k, is the index for the class. So let's look at this term, ynk to the power of tnk. Let's look at the label vector tn. For each training data n, its label vector is a Boolean vector. All the elements are 0 except the ground truth class. So if we consider every class this data not belong to, its power is always 0, so the corresponding term disappears. So if we just consider the inner product operator and the corresponding term, actually it will reduce to a single term, ynk to the power of tnk, if the ground truth class is lowercase k. So you can check the relationship. The second product operator is used to work with the label vector. So after the description, you can find that this is also the likelihood for the individual training data. 我用中文讲一次这一页投影片哦。我们在上一堂课呢，讲过了这个目标函数哦，就是这个训练资料它的目标函数。那它的因为它训练资料是 RID 的，所以我们这边有一个连乘的符号。 那我们之前呢是用到这个指数次方的搭配，这个 label 属于01的这个两个之间结合的这个 trick， 我们可以同时考虑这两种情况啊。那今天呢，我们要处理的是一个多类分类的问题，所以呢，任何一笔资料第 n 笔训练资料它的光数是 Tn， 那它的 Tn 呢，现在的表示方式呢，其实是一个Boolean vector。那这个 Boolean vector 呢，它的这个长度呢，是跟 class 你要处理的这个 class k 呢是一模一样的。我们今天如果要做五类的分类的问题的话，这个 Boolean vector 它的长度就是5维。那里面呢所有的 element 里面这个 vector 里面的所有的这些元素这些所有的 element 通通都是0除了正确答案除了 ground truth 的 class 比如说第三个 class 这个答案是正确的，答案是第三个 class， 所以它的第三个 element 就是其他的这个 element 通通都是0。那我们现在呢，这个 likelihood function 你可以看到呢，跟上面的不一样的是呢，你可以看到这个 W 原来2元分类我们只学一个 W 就是 class 1的对应到的 W。那今天呢，如果要做 K 类那我们刚刚按照我们用 softmax 的方式，我们需要学习的这个 weight vector 呢就是跟这个分类别数目是一模一样多一个 weight vector。然后一个 class 就会有一个对应的一个 weight vector。那这边的定义我们先讲它的定义，从第2个数学式到第3个呢其实是等价的那这个原因是因为我们接下来用 y、n、k 这种看起来比较简单的这种符号来缩写。那它的 y 呢，我们都知道它在算 posterior probability。那 n-k 是什么呢？它有2个 index。那 n 呢就是资料的 index， 第 n 笔训练资料。那 k 呢就是第 k 个 class。那你可以看到它的定义就写成这样子也就是呢第 n 笔资料属于第 k 个 class 的它的 posterior 就是这样子，就 y-n-k 就是第 n 笔资料属于第 k 个 class 的 posterior probability。所以这个叫 y-n-k。那从这边到这边来其实就是只是把这个符号带进来而已啦。你可以看到这前面就是第 n 笔资料在第 k 个 class 的 posterior probability。那所以我们现在呢要讲这一个数学式跟上面的这个数学式，从2元分类使用这个数学式到这个多元分类这个数学式之间的异同是在什么地方那因为资料都是 RID 的，所以呢，这个有一个连乘的符号，那是针对所有资料的 likelihood 算出来其实更精确来讲是所有训练资料的 posterior 做连乘而成。那这边呢，同样的道理这边因为资料就是 RID 的，所以我们第一个连乘符号。那我们先来看第2个连乘符号。那第2个连乘符号呢，可以看到它的这个它要连乘的对象呢是针对不同的 class k。那小 k 是 index， 那大 K 呢是 class 的数目。那我们来看在这里面呢，我们先看这个指数次方k 小 k 等于1到大 K， 所以我们考虑的是 Tn1、Tn2、Tn3类似像这样子这几个 term 的连乘。那什么是 Tn1、Tn2、Tn3、Tn4这些东西呢？其实就是在讲这一个 vector Tn 呢就是这个 vector。那你会发现呢，其实呢一大堆都是0，全部都是0，除了 ground truth 那个 element 是1以外，其他都是0。所以你在这边算什么 Tn1什么东西的 Tn1 次方、Tn2 次方、Tn3 次方这些呢通通都会是0，除了正确的那个 class。所以呢，这边算出来的结果呢，就是当 k 是你的正确的那个 ground truth 的 class 的时候，我们会保留它的 y、n、k。那如果 k 呢不是它的 ground truth 的时候，它就会就是指数次方就是0次方，就是什么东西的0次方不通都是1，那项就会消失掉。所以这一个第2个连乘的符号呢，这整体而言呢，虽然好像看起来你连乘了大 K 次，但是实际上只有1次的效果，ground truth 的效果，那一次 y、n、k 会留下来。 其他的通通都会消失掉。那这个呢，就是这个 tree 的多个类别的一个泛化的版本。Okay, so based on in the previous slide, we have defined the likelihood for multi-class classification. In this slide, we still consider negative log likelihood. So we still apply the log operator to the likelihood function. We also consider the negative sign to yield negative log likelihood. So it is also called the cross entropy error for multi-class classification. In the following, we are going to calculate the gradient and the Hessian matrix if we want to use Newton-Raphson iterative optimization to carry out the optimization process. So we need to calculate the gradient with each Wj for each class J, and we also calculate the Hessian with respect to Wj and Wk for each pair of classes J and K. So it is a bit complicated, but let's look at the dependency, the relationship. Objective function is cross entropy error, just like the two-class classification case. E is a function of y. Y is the softmax function to calculate the probability. And the y is the softmax function. It is a function of A, the input to the softmax function. And for each A, it is a function of W. The input to the softmax function A depends on the optimization variable W. So let's look at the three-level relationship again for multi-class classification. First of all, let's consider the relationship between E and Y. This is the cross entropy error or negative log likelihood. Its function is given here. So as you can see, the objective function E is a function of y and k. So it is differentiable with respect to y and k. So we can calculate this term directly. dE by dy and k. So the answer is straightforward according to its relationship here. Let's discuss the second level relationship y and yk and az here. So yk is the posterior probability for class K, and it is defined as a softmax function. And its input is az for each class J. So let's look at its partial derivative, the yk by the az. Yk is here and the az is here. To consider the derivative, we need to consider two cases. If j equal to k, because both j and k are the indexes of class. So if j is equal to k, so ak or az is present in both numerator and denominator. So this is this case. On the other hand, if j is not equal to k, so az is just present in the denominator. It is this case. So the derivative is straightforward. So if you combine the two results, this is the equation to consider the two cases. And IKY is defined here. So as you can see, the derivative is given here. 这一页的 这页的微分有一点点复杂，所以我用中文跟大家讲一次啊。那我们这边呢，主要是在算呢the yk by the az yk 在这边，那 az 在这边啊。那我们知道k 呢它是 class 的 index， 那 j 呢这个 normalization term 它也是 class 的 index， 所以你必须得考虑两种情况就是呢你的微分的对象呢，如果这个 j 的值呢，它可以等于1等于2，一直等于到大 K， 所以它会有一个比较巧的情况呢，就是 j 等于 k。所以你的微分的对象呢 ，j 等于 k 的时候呢，就是这个 aj 呢，同时也在分母出现，也同时在分子出现。那在这个情况呢，你的dyk by dak 呢，它的推导就在这边因为分子分母都有，所以它推导出来就是像这样这边是比较 straightforward 的。那另外一种情形呢，就是 j 不等于 k， 那这样子呢，分子呢就没有出现相关的aj 相关的东西，就只有分母出现而已。所以呢，这是另外一个这个 case 那这两个 case 呢，如果你要把它用一个数学式来表示的话就是这个数学式。我们定义呢iky 呢等于1跟等于0的情况分别就是它后面所写的这个情况。所以我们这边呢可以用这个第二阶的这个微分关系呢可以用这页投影片来表示。Let's look at the third label relationship. This is the relationship between wj and anj. Okay, so its relationship is straightforward. So as you can see, anj is a function of wj. So its partial derivative is phi n. It's straightforward. You can derive this equation. Now we would like to combine the three label relationship. Okay, so in the previous two slides, we considered dE by dy and k. In the previous slide, we considered dy k by dAj. In this slide, we also have the third relationship. If we combine all of them, it turns out that dE by anj is here. So you combine this one and this one, we complete the so-called chain rule. Okay, so by using the result given in the previous slide, we can still calculate gradient and the Hessian matrix. Similarly, we can use Newton-Raphson method to optimize logistic regression for multi-class classification. Okay, I know logistic regression is a bit complicated during optimization. So I made a slide to summarize what I talked about logistic regression today. So for two-class classification, we formulate the posterior probability for class 1, and we leverage the logistic sigmoid function. Okay, our goal is to learn the W, and we use negative log likelihood to serve as the objective function, and we use Newton-Raphson method to carry out optimization. Okay, so this is the formulation for Newton-Raphson method. And this method could be extended to multi-class classification. To summarize, this is a big chapter. We consider three types of linear classifiers, including linear discriminant. In this part, we specify three types we give three instances of linear discriminant, including two-class discriminant, k-class discriminant, and most importantly, we talk about Fisher's linear discriminant, which is a representative method in the field of machine learning. It is widely used in the literature. In the previous week, And this week, we respectively talk about generating model and the discriminating model. In my opinion, discriminating model is more powerful and is more compact. Based on the two major advantages, discriminating model is widely used in the literature. So in logistical regression, we formulate a posterior probability. We can use stochastic gradient descent or Newton-Raphson iterative optimization to derive the logistical regression model for classification. So I complete this chapter. If you consider the content complicated, I strongly recommend you to read chapters 4.1, 4.2, and 4.3 in the textbook. Is there any question? 这边跟这位同学强烈的建议哈，就是我们这门课会有期末考，那大家最好还是就是每讲完一个 chapter 可以跟着看一下这个教科书，以免到最后累积蛮多的。我们只有一个期末考而已，那是在第15周，那边的时候有可能会累积比较多的内容，所以我建议大家还是可以按部就班的去看一下这个教科书还有这个对照看一下通篇的内容。不晓得大家有没有什么问题？我再讲 neural network。Okay, let's move on to the next chapter.之前这门课是没有期末考的啦。你们这一届就是第一届需要期末考的大部分是不会为难学生啊。我知道很多老师都这样讲的这句话是不是真的？就你们自己看一看。我会考我上课教过的内容，也就是我讲的这些reference 的那些部分。所以作业请务必自己写，我会找 TA 说考那些作业的相关的题目。不过这也是拜你们的学长姐所赐就是没有考试的大部分大家分数都很高，都不晓得作业是不是自己做的这样子。Okay, in the following, I'm going to talk about a very important and powerful machine learning methodology, neural networks. In the previous few weeks, we talked about linear model for classification and the linear model for regression. In this chapter, we talk about neural networks. Actually, it is a general approach. By general, I mean that by neural network, by general, it means that neural network can be used for regression, for classification, or for other applications such as density estimation or one-class classification. So it is a general approach. By using different objective functions, neural network can be applied to various machine learning tasks. Also, neural network is not a linear model. Actually, we can learn the nonlinearity between feature dimensions. So it is a powerful machine learning methodology. Okay, to begin with, I would like to specify the relationship between linear model and the neural network. let's look at what is the natural difference between linear model and neural network or nonlinear model. So this is the objective. This is the formulation we consider in generalized linear model for regression or for classification. We consider this model given an input x, and we employ a set of nonlinear basis function to convert the feature vector nonlinearly to n-dimensional space. We use phi1 to project the data nonlinearly to the first dimension. We use phi2 to project the data into the second dimension. If we employ capital N nonlinear basis function, we project the data, project the feature vector x to n-dimensional space. Okay, so both linear model for classification and the regression, we focus on this formulation. It is a linear combination of nonlinear basis function. The key difference between regression and the classification lies in here on F. F is an identity function for regression. The decision value computed in the parentheses can be used for regression directly. The F should be a nonlinear activation function. For example, we use logistic sigmoid function to carry out two-class classification. We use softmax function to carry out multi-class classification. So this is the general formulation for linear model for either classification or regression. However, I would like to focus on this term, fixed. We need to predefine the basis function in advance. Before given any training data, we need to predefine or fix the basis function before optimization or during optimization. They are fixed, remain unchanged during optimization. So let's look at how to convert a linear model to a neural network. We consider two differences. The first major difference is that the nonlinear basis function should not be fixed. They can be controlled by some learnable parameters. They depend on parameter. Second, the parameter can be learned during training. In other words, the basis function are no longer fixed. They can be changed during optimization. Okay, so this is here are the two major differences between neural network and linear model. Here is a figure or an illustration for a neural network model. Actually, a neural network model is a layer-wise structure. The first layer, second layer, third layer, fourth layer, and then the last layer. For the first layer, it is often called input layer. So we consider a circle of neuron. So this is used to receive the input feature vector for classification or regression. The intermediate layer are called hidden layer. So in this neural networks model, there are three hidden layers. And the last layer is used for prediction or for output. There are 4 neurons in this example. So this model can be used as for 4-class classification or regression test with 4-dimensional output. So this is an illustration for neural network. In the following, I will focus on the 2 major differences. 在讲这个 neural network 的时候哈，其实呢，这本书写的蛮好的，就是 我们前面都是在讲这个线性的模型。那这个线性的模型呢，如果呢你把它做了两个根本上面的改变了以后呢，你真的有可能变成是一个就是两层的这个类神经网络哦。那等一下我们就是会告诉大家为什么呢做了这两个改变了以后呢，前面这个数学式前面这个大家应该都很熟悉的数学式，它会对应到一个两层的一个类神经网络。那这两个改变是什么呢？首先我们前面讲的那个每一个的那个 basis function phi 呢，它是由一堆参数来控制的，连 phi 本身都是由一些参数来控制的。那第二个呢，这个参数是可学习的，就是这两点不同。等一下会让大家去验证这个讲法。Okay, so I copy the equation we use frequently in the previous weeks. So in the following, I'm going to show you that this corresponds to a two-layer neural network. Actually, neural network can be generalized to multi-layers, but we consider this is a special case of two-layer neural network if we apply the two major changes to this equation. In the previous week, we talked about basis function phi 1, phi 2 to phi capital N. We have specified three types of widely used basis function, including polynomial basis function, Gaussian basis function, or sigmoid basis function. Their corresponding curve are given here, here, and here respectively. I would like to emphasize that those functions are fixed. The reason is that this function is controlled or parametricalized by its power z. In this function, its curve is controlled by mean and the variance mu z and the s. Similarly, in this basis function, it is controlled by mu z and the s. But we need to predefine the value of the hyperparameter in advance. In other words, the power of z remained unchanged, or the mean or variance remained unchanged during optimization. They are fixed. We would like to change that. Okay, so to begin with, let's focus on the counterpart in neural network corresponding to this part enclosed by the red rectangle. We consider one particular basis function phi j. The phi j, when we apply phi j to a feature vector x in a d-dimensional space, we project this d-dimensional vector to a one-dimensional space. So let's look at the corresponding part in neural network. If we focus on one particular training data in capital D dimensional space, there are capital D elements in this vector, including x1, x2 to x capital D. Because the basis function depends on some parameter, so we introduce learnable parameter here. AJ is called the activation. Is the activation. As you could check here, there is a sum operator. We apply the weight elements to the data element. We consider a linear combination of data elements by using the sum operator. Also, there is a bias term here. AJ is a real value. We code this value as activation. It is a linear combination. In this equation, WZI1 is are called weight. As you can see here, there are two indexes in the subscript. J is used to index the basis function. I is used to index the data dimension or data elements. So WJI1, there is a superscript in this notation. A superscript is used to index neural network layer. It will become clear later. So WJI1 and WJ01 are the learnable parameter. We call WJ1 as weights and WJ01 as bias. As you can see, there is another index J here. J is used to index the basis function. Okay, since we employ capital M basis function, so the range of J is between 1, 2, and capital M. Okay, so this is the first part, linear combination to calculate the activation. Actually, this basis function is nonlinear. To integrate the power of nonlinearity, in the second part, we apply a nonlinear activation function H here to each element J. So we nonlinearly transform the value Aj to Zj. So Zj is given in this way. And J is the index of basis function. Totally, they are capital N basis function. So they are called hidden unit. 这页投影片讲的就是在讲这个红色框框里面的它的在 neural network 里面对应的版本。那出题的 x 是一个 feature vector， 那非 phi j 呢是 dj 个basis